Let's start with something simple. A dimension is just a direction you can move in. You can move forward and backward, that's one dimension. A line has one dimension. An ant walking on a tightrope lives in a one-dimensional world. It can only go forward or back. It has no concept of left or right or up or down. Now let's add another direction. The left and right. If you can move forward, backward, and left, right, you are in two dimensions. A flat piece of paper is a two-dimensional world. A character in a video game, like the original Pac-Man, lives in two dimensions. It can move up, down, left, and right on the screen, but it can't jump out of the screen toward you. We live in three dimensions. We have forward, backward, left, right, and also up, down. We call these length, width, and height. Everything we see, touch, and interact with has these three dimensions. A cube is a good example of a three-dimensional object. You can move around it, you can see its different sides. Our entire known universe, as we experience it, is three-dimensional, so a higher dimension is simply another direction. A fourth spatial dimension would be a direction that is different from our three. It would be at a right angle to length, width, and height all at the same time. That's where our brains hit a wall. It's impossible to picture. We can't point in that direction. We can't imagine what it would look like. Our minds are built for a 3D world, just as the ant's mind is built for a 1D world. But just because we can't picture it doesn't mean we can't think about it. Mathematics allows us to describe it perfectly. To get a feel for this, let's use a famous thought experiment called Flatland. Imagine a universe that is completely flat, like a sheet of paper. The beings living there are two-dimensional shapes, squares, circles, triangles. They have length and width, but no height. They can't even comprehend the idea of up. It's not in their vocabulary or their experience. Now, imagine you, a 3D being, reach down and poke your finger through their paper world. What would they see? They wouldn't see your finger. They would see a small circle suddenly appear out of nowhere. As you push your finger through, that circle would get a bit bigger, maybe change shape slightly, and then shrink and vanish as your fingertip passes all the way through. To them, this would be magic. An object appearing from nothing, changing shape, and then disappearing into nothing. They would have no explanation for it. They couldn't see the rest of your finger, or your hand, or your body. Extending up into the third dimension, they can't perceive. If you were to pass a sphere through their flatland, they would see a point appear, which would grow into a larger and larger circle, then shrink back down to a point before vanishing. It would be a baffling event. A circle that changes its own size is impossible in their world. This is the best way to think about a fourth dimension. A 4D object interacting with our 3D world would seem just as magical and strange. A four-dimensional sphere, called a hypersphere, passing through our space, would first appear as a tiny point. Then it would grow into a sphere, like a balloon inflating. The sphere would get bigger and bigger, then it would start to shrink, collapsing back into a point, and then disappearing completely. It wouldn't be moving away from us. It would be passing through our dimension. We can also think about it by building up. A point has 0 dimensions. It's just a location. Move that point, and it traces a line. A line has 1 dimension. Now, take that line and move it in a new direction, perpendicular to itself. It traces a square. A square has 2 dimensions. Take that square and move it in a new direction, perpendicular to its surface. It traces a cube. A cube has 3 dimensions. Now comes the leap of faith. Take that entire cube and move it in a new 4th direction, perpendicular to all its other directions. It traces a 4-dimensional cube. We call this a tesseract, or a hypercube. We can't see a tesseract, but we can see its shadow. Just like a 3D cube can cast a 2D shadow on the ground, a 4D tesseract can cast a 3D shadow. That shadow often looks like a small cube inside a larger cube, with the corners connected. When a tesseract rotates in the 4th dimension, its 3D shadow would seem to morph and turn itself inside out in ways that defy our 3D logic. So, we can describe it mathematically. We can imagine its effects on our world. But this all sounds like a fun mental exercise. Is there any reason to believe higher dimensions are real? It turns out there is. For over a century, some of our most important physics theories have suggested that they might be. It started not as a wild guess, but as a way to solve a very difficult problem. The problem was trying to unite the fundamental forces of nature. In the early 1900s, we knew about 2 main forces: gravity, described by Albert Einstein's new theory of general relativity, and electromagnetism, which governs electricity, magnetism, and light. They seemed completely different. Gravity was about the warping of space and time. Electromagnetism was about fields and charges. They were described by different sets of equations. Physicists dream of finding a single, elegant theory that can describe everything. a theory of everything. In 1919, a little-known mathematician named Theodore Kaluza had a strange idea. He took Einstein's equations for gravity, which worked in 4 dimensions, 3 of space, 1 of time, and just for fun, he rewrote them for 5 dimensions, 4 of space, 1 of time. He wanted to see what would happen, and something incredible happened. Out of the math, a second set of equations popped out. Those equations were the exact known equations for electromagnetism. It seemed like magic. By adding 1 extra spatial dimension, he had accidentally unified gravity and electromagnetism. But this raised a huge question. If this 5th dimension is real, where is it? We can't see it, and we can't move in it. A few years later, a physicist named Kaluza-Klein came up with an answer. Maybe the extra dimension is there, but it's incredibly small. He suggested that at every single point in our 3D space, there's a tiny, curled-up circle of a 5th dimension. The best analogy is a garden hose or a long cable. From far away, it looks like a one-dimensional line. You can only see its length. But if you get very, very close, you see it has a second dimension, the circular surface you can travel around. The universe could be like that. The dimensions we experience, length, width, and height, are huge and obvious. But there might be other dimensions curled up into a space so small we could never notice them in our daily lives. So small that only a subatomic particle could ever experience them. This idea, called Kaluza-Klein theory, was revolutionary. It suggested that dimensions could come in 2 types: large ones that we see, and tiny, compactified ones that are hidden. For decades, it was mostly a mathematical curiosity, but then came an even more ambitious theory: string theory. String theory is one of the biggest modern attempts at a theory of everything. It says that if you could zoom in on any fundamental particle, like an electron or a photon, you wouldn't find a tiny 0-dimensional point. Instead, you'd find a tiny 1-dimensional vibrating loop of energy, a string, and the way the string vibrates determines what kind of particle it appears to be. A certain vibration makes it look like an electron. A different vibration makes it look like a photon. Another one makes it look like a quark. All the different particles and forces in the universe are just different notes being played on these fundamental strings. It's a beautiful and elegant idea, but it comes with a condition. The mathematics of string theory only works if the universe has extra dimensions. It doesn't work in our familiar 3 spatial dimensions. The equations fall apart. Depending on the specific version of the theory, it requires 10 or 11 total dimensions, which means 9 or 10 spatial dimensions plus 1 of time. Just like in Kaluza-Klein theory, the idea is that these extra 6 or 7 dimensions are curled up and compactified at every point in space. But they aren't necessarily simple circles. They could be twisted into incredibly complex 6-dimensional shapes called Calabi-Yau manifolds. The specific shape of these hidden dimensions is very important, because it would determine the way the strings can vibrate. And that, in turn, would determine the fundamental laws of physics and the types of particles that exist in our universe. So, according to string theory, the reason our universe has the physical laws it does is because of the geometry of these hidden extra dimensions. There's another, even wilder idea that also comes from string theory called brane cosmology. A brane is short for membrane, and it can have any number of dimensions. In this model, our entire 3-dimensional universe might be a 3-brane, like a giant sheet floating in a higher dimensional space called the bulk. Think of it like a slice of bread in a loaf. Our slice, our universe, has 3 dimensions, but it's just one slice in a much larger, higher dimensional loaf. In this scenario, the extra dimensions don't have to be tiny and curled up. They could be huge, even infinite. So why don't we see them? The idea is that most of the fundamental particles and forces, like the ones that make up us, and light are stuck to our 3-brane. They are like ink drawings on a sheet of paper. They can move anywhere on the paper, but they can't leave the paper and float off into the 3D room. But there might be one exception: gravity. String theory suggests that the particle responsible for gravity, the graviton, isn't stuck to our brane. It can travel freely through the bulk. This could explain a major mystery in physics. Why is gravity so much weaker than the other forces? Electromagnetism is trillions and trillions of times stronger than gravity. You can see this yourself. A tiny refrigerator magnet can lift a paper clip, defeating the gravitational pull of the entire planet Earth. The brain world idea suggests that gravity isn't actually weak. It's just as strong as the other forces, but its influence leaks out into the extra dimensions. We only feel a tiny sliver of its true strength, because most of it is spread out across the higher dimensional bulk. This is a testable idea. If gravity does operate in more dimensions, it should behave differently at very small distances. The familiar inverse square law of gravity might break down, so we have these compelling theories from physics that all point to the possible existence of higher dimensions. That brings us to the big question. If they exist, could we ever access them? Let's look at the possibilities, from the most plausible to the most speculative. The most direct way we are looking for them is with particle accelerators, like the Large Hadron Collider LHC in Europe. The LHC smashes protons together at nearly the speed of light. The goal is to concentrate a huge amount of energy into a tiny space to create new exotic particles. If the large extra dimensions of the brane world model are real, some of the energy from these collisions might be able to create particles that can travel off our brane and into the bulk. Specifically, it might be possible to create tiny, short-lived black holes. These wouldn't be the giant, world-eating black holes of space, but subatomic versions that would evaporate almost instantly. How would we know if we made one? We would look for missing energy. When particles collide, we know from the laws of physics that energy and momentum must be conserved. We carefully measure all the particles that fly out of the collision and add up their energy. If the total energy after the collision is less than the energy before, it means something carried that energy away without us detecting it. One possibility is that a graviton was created, and it shot off our brane into the higher dimensions. So far, the LHC has run countless experiments, and we haven't seen any definitive evidence of missing energy that points to extra dimensions. But the search continues. Another way is to test gravity at very small scales. As mentioned, if there are large extra dimensions that only gravity can access, then gravity should get much stronger at distances smaller than the size of those dimensions. Physicists have built incredibly sensitive experiments to measure the force of gravity between two objects that are micrometers apart. These are very difficult experiments because gravity is so weak and other forces like static electricity can easily interfere. So far, these experiments have confirmed Newton's law of gravity down to very small distances. We haven't found any deviation that would suggest gravity is leaking into another dimension. Those are the methods based on current, testable science. They are about detecting the influence of higher dimensions, not actually entering them. What about travel? Could we ever move into a fourth spatial dimension? This is where we leave the lab and enter the world of theoretical physics and speculation. To do this, we would need to somehow manipulate the fabric of space-time itself. The most famous concept for this is a wormhole, or an Einstein-Rosen bridge. A wormhole is a theoretical shortcut through space-time. The classic analogy is to take a piece of paper and mark two distant points, A and B. An ant walking on the paper would have to walk the long way across the surface. But if you could bend the paper through the third dimension and touch A and B together, the ant could step across in an instant. The wormhole is that bridge. It connects two distant points in our 3D space by creating a tunnel through a higher dimension. General relativity allows for the possibility of wormholes. The math works out. But there's a huge catch. To keep a wormhole open and stable enough for something to pass through, you would need a huge amount of something called exotic matter. This is a hypothetical substance that has negative energy or negative mass. It would essentially have anti-gravity, pushing space-time apart instead of pulling it together. We have never observed any exotic matter. We don't know if it can exist, and we certainly have no idea how to create it. So, for now, travel through wormholes remains firmly in the realm of science fiction. But what if we didn't need to travel? What if we could just de-reach? Let's go back to our Flatland analogy. As a 3D being, you can interact with the 2D world in ways that seem impossible to its inhabitants. You could lift a Flatlander right off their page, and to their friends, it would look like they just vanished. You could then place them back down somewhere else, and they would have teleported. You could look inside their closed houses from your above perspective. You could even perform surgery on them without cutting their skin, by reaching inside them through the third dimension. Now, apply that logic to us. A hypothetical 4D being could do the same things to us. It could see inside any closed room, any bank vault, any person. It could reach into a locked box and take something out without opening the lid. It could reach inside your body and touch your heart without breaking your skin. If a 4D being wanted to, it could make you disappear from our 3D space entirely by lifting you up into the fourth dimension. You would simply vanish. To us, its actions would seem like miracles or magic. It would be able to appear and disappear at will, just like your finger did in Flatland. A piece of it would enter our space, and we would see a 3D object materialize out of thin air. Then it would be gone. This is, of course, pure speculation. There is no evidence for any such beings. But it's a powerful way to understand what it would mean to access a higher dimension. It's not just about moving in a new direction. It would fundamentally change the rules of what is possible. It would give access to the inside of everything. So where does that leave us? We have strong hints from theoretical physics that our universe is more than what we see. Theories that try to explain the fundamental nature of reality, like string theory, almost demand that higher dimensions exist. They offer elegant explanations for why the universe is the way it is. They suggest that the most basic laws of physics are written in the geometry of these hidden dimensions. Physical proof. Every experiment we've designed to find them has come up empty. No missing energy at the LHC, no weird gravity at small scales, nothing. This doesn't mean the theories are wrong. It might just mean the dimensions are curled up even smaller than we thought, or that their effects are too subtle for our current instruments to detect. It's a strange and frustrating position to be in. The math is beautiful, the ideas are compelling. But reality remains silent. Science requires evidence, and in the case of higher dimensions, we don't have it yet. Could we ever access them? If we mean detecting their effects in a lab, maybe. A future, more powerful particle accelerator might one day find evidence of energy leaking away. A more sensitive gravity experiment might find a tiny anomaly. That would be one of the greatest discoveries in human history. It would confirm that the world we see is just a shadow of a much larger, more complex reality. If we mean consciously perceive or travel into them, the answer is almost certainly no, at least not in any way we can currently imagine. Our bodies and brains are 3D structures. We are built of 3D matter, evolved to navigate a 3D world. Experiencing a fourth spatial dimension might be as impossible for us as it is for a square in Flatland to comprehend. We might be like fish who have no concept of the world above the water surface. We can't even imagine what it would be like. And yet, the idea continues to captivate us. It speaks to a deep human desire to believe that there is more to reality than what we can see and touch. That our familiar world of length, width, and height is just one level of a much grander, more mysterious structure. The search for higher dimensions is, in a way, the ultimate exploration. It's not about traveling to a distant planet. It's about discovering whether our entire universe is just a small part of something else. For now, those extra dimensions remain hidden, either curled up in the fabric of space at a scale too small to probe, or existing as a vast reality that we are forever stuck within, unable to perceive. We don't know the answer, and for a scientist, not knowing is the most exciting place to be. It means there is still something incredible left to discover.